Welcome back to Educator.com and multivariable calculus. So today's topic, we're going to start talking about triple integrals. And the nice thing about it is there's actually nothing new to learn. You're just integrating 3 times. That's it. So let's just jump right on in and do a quick couple of words, and then we'll just get right to the examples because that's what's important. Okay, so for single integrals, we integrated over a length, either a length, the x-axis, or line integral, some path, but we integrate along a length. For a double integral, we integrated over an area, a 2-dimensional region, either a square or some other region. Well, for triple integrals, we're now integrating over a region in 3 space, which is a volume. That's all it is. We're still just going to integrate one variable at a time. So let's just start with an example, and I think it'll make sense. So the important thing with these triple integrals and double integrals and all integrals is being able to construct the integral. Taking a look at what your region is, being able to see this variable is going from this number to this number, this variable is going from this number to this number. That's what's important. Now, when you take your tests, of course, the integrals that you have to deal with are not going to be altogether that complicated. They can't be, because you only have a limited amount of time to solve it. What your professors want to see is that you can construct the integral. That's what's important. When you're doing your homework or other projects, mathematical software can do the integration for you, but it can't tell you what to integrate. That's your job. That's what's important. That's the skill that you want to develop. The integration part, that's incidental. Anybody can do that. You want to be able to develop the skill. So when you're doing these problems, don't worry about the integration so much. Worry about the region. What region am I integrating over? What are my values? What's my lower limit of integration? What's my upper limit of integration? That's where you want your emphasis to be. Okay, so example 1. You know what? I think I'm going to use blue ink because I like it. All right. Example 1. Okay, find the volume of the region bounded by, and again with these triple integral problems, the problems themselves can be worded in all kinds of ways. Sometimes they'll give you the equations explicitly. Sometimes they'll say it's bounded by this, bounded by that. You have to work out the equation. So there's no one way that you're going to see these integration problems. Region bounded by the xy plane, the yz plane, the xy plane, I'm sorry, the xz plane. I have xy, I have yz, I should have xz. There we go. The xz plane and the sphere of radius 3. Centered at the origin. Centered at the origin. So in this particular case, they didn't really give us a lot of information. There's no real equations. They're just giving me things by which it's bounded. They're expecting me to know that, the equation for the radius of a sphere of radius 3, the xy, yz, xz plane. So let's talk about what this looks like. So I have this. Let me draw my 3-dimensional xyz coordinates. This, and this. So this is going to be my y-axis, this is my x-axis, and this is my z-axis. So the xy plane, that's this thing right here. The yz plane, that is going to be this right here, the yz plane, and then of course the xz plane. So I'm bounded from below, from this side, and I'm bounded by the sphere of radius 3. Well, from the origin, if I have a sphere of radius 3, so I'm going to have that, and then that, and then that. So basically, it's the portion of the sphere only in the first octant of 3-dimensional space. So that's it. That's my particular region. That's the region that I'm looking at, is this sphere in the first octant. So my volume, well, by definition, the volume of a 3 using triple integrals, the thing that we're integrating, the function that we're integrating is 1. dx, dy, dz over this region R. That's the definition of volume. In other words, there is no function in the integrand. The function 1 suffices. That is the function that you're integrating. So now what we need to do is we need to find the region, our upper and lower limits of integration. Okay, so let's go ahead and draw the xy plane. Let's just look at the xy plane first. So this is y and this is x. Well, we have this sphere, right? So the z-axis is coming straight out and going straight down. Well, this is x squared plus y squared equals 3 squared. That's the equation of a circle in the xy plane. So now, what I'm going to do, 0 and 3. So as far as the x variable is concerned, x is going to go from 0 to 3. The y variable, well, y is changing. The height is changing. So y is going to run from 0 to this equation, which I have to express explicitly in terms of x, which becomes radical 9 minus x squared, right? If I take x squared plus y squared equals 9, I move the x over, I get 9 minus x squared. I take the square root, I get plus or minus. Minus gives me the part below, the plus gives me that part. So x goes from 0 to 3, y goes from 0 to 9 minus x squared. Now z. Well, z, the equation for the sphere is x squared plus y squared plus z squared equals 9. Well, I need everything above the xz axis, so z is going to be 0. It's going to be the lower limit of integration, and it's going to go all the way to, well, the sphere. Z squared equals 9 minus x squared minus y squared, so z equals plus or minus 9 minus x squared minus y squared. I take the plus version because I don't want everything below the xz plane. I want everything above it because I need, right, I go up. So it is going to be radical 9 minus x squared minus y squared. This is what's important. I need to be able to express the region. I'm integrating x from 0 to 3. I'm integrating y from 0 to 9 minus x squared. And I'm integrating z from 0 to 9 minus x squared minus y squared under the radical. In other words, I go in the x direction, go in the y direction, then I integrate in the z direction, depending on what my boundary is. So now I have my integral. So the volume, excuse me, is going to equal the integral from 0 to 3. That's going to be my x. It's always good to keep track of what's going first, second, third, because you're going to work your way working inside out. So the integral, y is going from 0 to radical 9 minus x squared. That's y. And z is going to go from 0 to radical 9 minus x squared minus y squared. And of course, our function is 1. We're going to do dz, dy, dx, right? Inner to outer, xyz, zyx. We're integrating in that direction. Well, when you put this into your software, you get 9 halves pi. That's it. That's the volume of that region. Okay, let's do another example. Let's see here. So example 2. Example 2. find the integral of f of xyz is equal to x y squared z cubed over the region bounded by the xy plane, the function y equals x squared, the function y equals x, and z equal to x squared plus y squared. So this time they gave us some specific equations to work with. So let's go ahead and draw out this region. And again, it's always best to start with the things that are easiest. So in this case, they gave me y equals x squared and y equals x. So let's go ahead and draw out the xy plane first. So xy plane, okay, so this is x, this is y. Y equals x squared, that's going to be that thing. Y equals x, that's going to be that thing. So this is 0 and 1, that's where they meet. So this is the particular region. So as far as, we take xy plane, y equals x squared, y equals x. So this xy plane means that the z value is going to be 0, and then the upper value of z is going to be x squared plus y squared. So we're going to integrate along x from 0 to 1. We're going to integrate along y from x squared to x, and then we're going to integrate up z from 0 to x squared plus y squared. So just to draw out what this looks like, now let me draw it out in 3 dimensions. So again, now this is y, this is x, and this is z. Well, in the xy plane, we have the parabola, we have that. This is this region right here. Now, of course, we have the paraboloid. So everything over this up to this surface, that's what we're doing. That's our region, and we're going to integrate this function over that region. So let's go ahead and see what x and y and z are. And again, it's always good to write them out specifically. So x, it's going to go from 0 to 1. From 0 to 1. Y is going to go from x squared to x, right? The x squared is the lower function. X is the upper function. And z, that one is going to, these are not equal signs. These are colons. Colon, colon, colon. Z is going to go from 0, because it's bounded by the xy plane, all the way up to x squared plus y squared. So there you go. So our integral is going to equal, so 0 to 1 for x, x squared to x for y, 0 to x squared plus y squared, squared plus y squared. We have x, we have y squared, we have z cubed, and now this was x, this was y, this was z. So we're going to integrate dz, dy, dx. dz, dy, dx. And again, the actual order itself doesn't matter. It just depends on what the problem is at hand. Sometimes it might be easier to do the dy first, or the dz first, or the dx first. It doesn't really matter. What you have to be able to do is look at your region and see what's going to give you the easiest integration. That's it. And then when we go ahead and put this into our math software, we get this really wacky number, but it is just a number. 6,401 over 411,840. That's it. Perfectly valid number. So the integral of this function over this particular region of space is this number. That's it. What's important is being able to construct this integral. If on a test you're pressed for time and you can't actually solve the integral, move on. Most of your points are going to come from being able to construct this integral. I promise you, there's no teacher that's going to punish you simply because you couldn't do the integral. But you will get lots of points taken off if you can't construct the integral. They understand that. Be able to do this, you'll get most of your points. Okay. Let's go ahead and evaluate an integral by hand just so you see what this single-step manual process looks like as opposed to putting something into mathematical software. So I just want you to be able to see it one time at least. So this one we will do by hand. So example 3. And of course the function can't be that complicated because we can't be here for 30 minutes solving an integral. Okay, so f of x, y, z is going to be a rather simple function. We're just going to go with x. That's it. Okay, x. And the region is the same region as the previous example. Is the same region as the previous example. Okay. So our integral is going to look like this. Our integral is going to be from 0 to 1, and it's going to be from x squared to x, and it's going to be from 0 to x squared plus y squared, and this time it's just x, and again we're going dz, dy, dx because we did x, y, z, moving from inside out. Okay, let's go ahead and deal with the first integral here. So this is going to be this integral right here. And I'm going to go ahead and pull the x out because here the x is constant. I'm integrating with respect to z first. Let me do this in red. I'm integrating with respect to z first. So x is constant. I'm just going to pull it out of the integral. So we get 0 to x squared plus y squared of just plain old dz. Well, that's going to equal z going from 0 to x squared plus y squared. And my answer is x squared plus y squared. Well, there's this x here, so I'll put it over here, and I'll go ahead and multiply it out. I could carry the x, I could keep carrying it back. It's not a problem. I don't have to multiply it out. It's just my personal taste. I like to go ahead and deal with what I can deal with right away, rather than pulling it out as a constant. And again, there's no one way to solve these. It's just a question of personal taste. So I'll go ahead and multiply this out, so I end up with x cubed plus y squared, I'll write it as xy squared, how's that? So x cubed plus x y squared. That's it. So now this thing is going to be my new integrand for my second variable. So I've taken care of that one. So now I'm going to go ahead and drop this in here. So I'm going to get the integral from x squared to x of x cubed plus xy squared, and this time we're integrating with respect to y. So dy. Well, again, x is a constant. I'm integrating one variable at a time. So this becomes x cubed y plus x times y cubed over 3. And this time I'm going from x squared to x. And now when I put these values in, I'm putting these in for y, okay? X is a constant. Remember, these values are integrating with respect to y. So this x goes into y. So when I do this, I get the following. I get x to the 4th plus x to the 4th over 3 minus x to the 5th plus x to the 7th over 3, which ends up equaling x to the 4th plus x to the 4th over 3 minus x to the 5th minus x to the 7th over 3. So that's my new integrand for my last integral. So now I'm going to integrate from 0 to 1 of, well, x to the 4th plus x to the 4th over 3 minus x to the 5th minus x to the 7th over 3 dx. And I end up with the following. I should get x to the 5th over 5 plus x to the 5th over 15 minus x to the 6th over 6 minus x to the 8th over 24, and I'm integrating from 0 to 1, and when I put 1 and 0 into there, I get the number 7 over 120. That's it. When you're doing this by hand, you just take it one variable at a time, remembering to hold all of the other variables constant. That's all you're doing. Just integrate slowly and carefully. Now, are you going to make mistakes? Of course. There's a bunch of symbols floating around. There's a bunch of numbers floating around. But you want to do as many problems as possible just to become accustomed to actually doing these. They do take a little bit of time. But again, you're not going to get anything complicated on a test because you just don't have the time. I mean, look, it took nearly 5 minutes to do this integral. You don't have that 5 minutes. Constructing the integral, that's what's important. Okay. So let's do a final example here. So this is going to be example number 4. We will let our function f of x, y, z equal some trigonometric function this time, x, z times the cosine of x, y. So that's going to be the function that we want to integrate. And we want to find the integral of f over the region bounded by y equals the sine of x, y equals 2 sine of x, x squared plus y squared plus z squared equals 4, and z greater than, oops, sorry, not greater than or equal to, and z less than or equal to 0. Okay, so these are our boundaries. Y equals sine x, y equals 2 sine x, x squared plus y squared plus z squared equals 4, and z is greater than or equal to 0. Okay, so we're going to have everything below the the xy plane, because z is going to be negative. So let's go ahead and deal with the xy plane first. So let's just see what this looks like. So we have y equals sine x, so that's going to be that graph right there. Y equals 2 sine x, that's going to be that graph right there. Sorry, my hand is a little shaky there, but you know what the graph looks like. So it looks like x is going to run from, x is going to run from 0 to pi, from here to here, because we're looking at this region in the xy plane. Z is less than 0, so it's going to be everything below this plane. And x squared plus y squared plus z squared equals 4. That is the sphere of radius 2. So that's what you've got. So now let me draw this in 3 dimensions as well as I can. It's kind of difficult. And again, you don't necessarily need to see it. If you have all this information, if you have the kind of a mind that can sort of pick out what's going where, you don't need to draw it out. So remember, this is, oops, crazy lines again. I love those things. Okay, so this is x, this is y, this is z. So y equals x, so we have, that's sine x, that's sine 2x, so this is the region. And then of course we have everything below that, so we have the sphere. It's a little weird, I know. You know what, I'm not doing a very good job drawing it, but you know what's happening. It's basically this region, everything below the xy plane touching the sphere x squared plus y squared plus z squared equals 4. So, okay, so now let's go ahead and recall what's going where. So x, we said, is moving from 0 all the way to pi. Well, y is moving from sine x to 2 sine x. So sine x to 2 sine x. That's lower and upper. And z, well, z is going from minus radical 4 minus x squared minus y squared up to 0, right? The lower limit of integration is the actual sphere itself, and it's going up to 0 because it's below the xy plane. So this is what's important. So now our integral is going to equal the integral from 0 to pi, the integral from, oops, not 0, the integral from sine of x to sine of 2x, and the integral from minus radical 4 minus x squared minus y squared up to 0. And then, of course, we have our function, which is xz cosine xy. And again, this is x, this is y, this is z. So we're working out. So we're going to do dz, dy, and dx. And when we put this in our software, we get the following number, 13.657. Again, perfectly valid number. So when you're doing these integrals, this is what you want. You want to be able to construct the integral. You want to be able to, you're going to integrate along x, you're going to integrate along y, and then you're going to integrate along z, or I'm sorry, x, y, and z. 3 things you need to be able to put. You need to be able to choose these things. That's what's important. The rest is just integration. Okay, so that is our introduction to triple integrals. In the next couple of lessons, we're going to be talking about cylindrical coordinates and spherical coordinates and triple integrals in those particular coordinate systems. Thank you so much for joining us here at Educator.com. We'll see you next time. Bye-bye.